mean, y'all know their drill now, that it's on chapter 6 and 7. So study the notes, read the book. By the way, I want my books back tomorrow. And you won't get your grade in the class until I get my book back. So if you've lost it or whatever, we can talk about that, how you can go about replacing it. But I'm not going to post your grades until I get the book back. Like, you'll just get an incomplete. So I'll send an email to that effect. It's about half and half, chapter 6 and 7, maybe a little bit more chapter 6. I think we just spent more time on chapter 6. So you'll need to know sort of the basics about light. That light is a wave. It's a transverse wave with all these speed, wavelength, frequency, all that stuff. You need to know the electromagnetic spectrum and the order for energy and wavelength. You need to know the light, the visible spectrum, Roy G. Biv, and the energy, that is that blue light has a higher energy than red light. You know how light is formed by the motion of electrons, in particular visible light by electrons moving in and out of energy states. You know the wave front and the ray model for light, and when that applies. You're going to have some geometric optics. You need to know how to calculate the speed of light, that if I give you an index of refraction, can you calculate the speed of light in that medium? We've done problems like that. You're going to need to interpret one or more of these type diagrams, and I'll ask you where is the speed higher, where is it lower, and also what is the index? Is the index bigger or smaller here? We can look at something like that. So I'm just sort of giving a quick overview here. There's some. Need to know the different types of lenses, both be able to define them by shape, like these four lenses, and then also be able to define them by converging, diverging. You see questions like that on the old test, and you'll see them tomorrow as well. Know how to define focal point, real and virtual images, what those are, and what the difference between them. As I said, converging and diverging lenses, and then also focal length. Know how to calculate the power. Pretty sure you have a question. I'll just give you the focal length. The power is just the inverse of that. And then the thin lens equation. You don't have to do any calculations with the thin lens equation, but it can be useful if I'm looking at things like what happens with the object distance, then what happens to the focal length in the human eye, right? Because in the human eye, the image distance is constant. And so what happens to that focal length if you change the object distance? That's on there. Everything's on there. Everything I'm saying is on the test. The ray diagrams, I'm going to ask you questions about that, but they can be useful in helping you to think about it. A lot of A and P of the eye, so make sure you know all the parts of the eye, what they do, and what they're called. Know the different layers of the eye, the sensory, the vascular, the fibrous, what those layers do, the different parts of the eye, like the fovea and the optic disc, the liquid. I don't get into that because we covered that in the chapter on fluids, so don't worry about the liquid in the eye. And then the path of the light into the eye and comparison with a camera. We talked about that, and then we watched that video too, sort of how are they similar and how are they different, that the focal length of the eye changes, the image distance of the camera changes. Near and far point, know what those are. Those are the nearest that you can see and the furthest that you can see, and how those change with age. Know the vision problems, nearsightedness, that means you can see close up, that's called myopia. And then farsightedness, you can see far away, that's hyperopia. And then also presbyopia. I crossed this out, that's not on the exam. What these other things are. Make sure you know all these various problems. Make sure you know also what corresponds to what. Like, for example, the farsightedness means that your eyeball is too short, and nearsightedness means your eyeball is too long. Know those, okay? See a question about that, I'm pretty sure. Presbyopia, astigmatism. Okay, so that's chapter 6. We can go back, we'll look at some old tests, and if you have any specific questions about it, we'll go back and look at that. Let's go ahead and look at chapter 7. My big warning to you on chapter 7 is, as you're practicing old exams, that the new material isn't on those old exams, so go back and make sure you're comfortable with that. I pulled questions directly from the notes, so if you know the notes, it won't be a big deal. Yeah, Hannah?
Why do you say new material? You mean like this?
Yeah. Right, there's sheets that I printed out and we filled in. Those videos are online, so if you've forgotten that, you can go back and look at it. Okay, so this is chapter 7. Know about radiation. Make sure you know the difference between alpha, beta, and gamma. That alpha and beta particles are particles, and gamma rays are radiation, actual light. Also X-rays, UV, Vis, those can all be ionizing, although to a lesser extent. So you know the models of the nucleus, and then also that the nucleus is made up of, protons and neutrons. The planetary model, the shell model, and the nuclear shell model. These are two distinct models right here, the nuclear shell and the shell model. I think on a quiz I might have asked you to rank them or whatever, but I realize that that's kind of confusing, so you won't see those together. They're similar but different. You understand what I'm saying? You don't have to distinguish between the shell and the nuclear shell. So you know the nucleon, lots of reactions, decay equations, and then also, where is it? Was it on this previous page? Yeah, your atomic notation, your atomic number and your atomic mass number. Oh, here it is, your nuclear notation. So how do you interpret these numbers? So make sure you know that, because that's important for your decay equations, and then there'll probably just be specific questions. How many neutrons are in this atom? How many protons are in this atom? You'll need to use the periodic table too. I'll give you a periodic table. It's the same one that's in the back of your book. You will need to know the names, or you don't need to know the names, but I'll give you the name of an atom, and you need to be able to find it on the periodic table, which isn't hard. It just takes a little time, to look at it. But just make sure you're aware of that. And then I might also give you the atomic number, and you have to give me the atom, the name of the atom that I'm referring to. So make sure you know that notation. Talk about stability, how when your nucleus gets too big, it becomes unstable. And then the types of nuclear radiation. So you'll have 6 or 7 decay equations where I'll either describe what is the decay that's occurring, electron capture, beta positive or minus positron, or beta minus decay, or alpha decay. And you'll need to know how to figure out what is the daughter nucleus, or I might ask you what is the missing particle or whatever, or radiation in this equation. Well, we've done those before. Or maybe how many neutrons or how many protons are in the daughter. So make sure you know those, because that's going to be a big 5, 6, 7 questions out of 48 total. So that's significant. That's more than a letter grade. Okay. There's some good examples here: alpha, beta minus, beta plus, and electron capture. So you know all those. We can do some practice on that. They will be new questions, so practice those old tests, but they will be new decay equations. If you're struggling with them, just Google, hey, alpha decay or beta minus decay. You can find more examples online. Okay, yeah, all this, I already talked about all this. Make sure you just know what the beta minus, beta plus, alpha decay, and electron capture are, just what they're doing in words. That alpha, beta minus, beta plus, those are all getting rid of something, and electron capture is the nucleus is taking on something. So that's the big difference in those. Okay, this is a good table. We filled this in that has all the different types of decay, nuclear decay. Okay, and then the effects of radiation on humans. Stick pretty closely from here all the way to the end, pretty closely to the notes. So actually really closely to the notes. So make sure you just go through and know these parts. And let me open up that other section, the radiation section. So, sure you know the difference between dose and effective dose? The difference in those? My computer is. The relative biological effectiveness, which is largely the difference between the effective dose and the dose. Also realize that some particles, even if they have the same energy per mass, that they can do more damage. And the alpha particles, which are big and move more slowly, they just have more time to hang around in your body, so they do more damage. And this is not working. Oh, there we go. Okay. So just review this. You'll see some examples of these. I don't expect you to know these numbers, but just review these notes, these few pages of notes. You do need to know the different applications. The cancer treatment or the external devices, the gamma knife, the cyber knife, be able to identify those by what they do, okay? The brachytherapy, make sure you know what that word means, where they actually put these, these little beads or pellets of radioactive material in or near the tumor in your body. The pain treatment, where you have these palliative agents. Heart disease, remember we talked about angioplasty. After they do angioplasty, they open up that artery. They'll embed nuclear material in the end of the stent. That just keeps plaque from forming there and prevents stenosis. Make sure you know these diagnostic techniques: single photon emission SPECT, or PET, positron emission, X-ray, and CT CAT scans. Sure you know what each of those four are, okay, what they do, and what type of particle they're using. It's all nothing more than what's here in the notes, but there are videos there that you can watch. They're also online. And then make sure you know other uses: nuclear power. For example, Waterford 3 is our nuclear power plant in Louisiana. Did y'all know that? Waterford 3 is our nuclear power plant. It's not far from here. It's about 45 minutes. It's on the river. Carbon dating and food irradiation. Okay, so that's a quick rundown of chapter 6 and 7. Everything's on the test, so there's not really anything to not cover. But are there specific questions that you want to look at? Yeah. Brooke, right? Brooke? Oh yeah, so an electron volt is a form of energy, 1 eV. That's an electron volt. It's a form of energy that we often use to talk about electrons moving around in an atom, because, I don't know, it's just, if I have one electron and it moves across a distance or a potential difference of 1 volt, the amount of energy required for it to do that, for it to move from here to here, the change in energy for that is equal to 1 electron volt. So that's how we define that. But often when we look at electrons changing energy states, remember we have our nucleus, and then we have these energy states. As electrons move from one energy state to another, the change in energy for those is usually, a handful of electron volts. So it's a nice, convenient unit that we can have to talk about electrons changing energy states. So 2 things that you need to know. One is that an electron volt is the energy change in an electron that moves across a potential difference of 1 volt. So you'll see electron and you'll see volt. Those are key words. And then the second thing is that energy is often associated with electrons changing energy states. So that's another key word, energy states. And that's why we use it, because it's just a convenient unit to use. Okay? Other specific questions? Anna, do you have your hand up? No. Danny? We can, yeah. Gabby, what did you?
I was gonna ask if you do one where it predicts where the light would move at,
Okay. All right. Yeah, so let's look at decay equations first, then we'll come back to that, okay? I'm going to go to the website. Unfortunately, there aren't many exams that have Chapter 7. Well, where is there a Chapter 7? Okay, here we go. So this is the spring 16. So you'll see several types of questions, and there'll be a lot like these. Like, for example, this one, number 43, just what type of nuclear decay is this? Right away, I can tell that this is electron capture. The reason I can tell that it's electron capture is I have this beta minus particle. Really, it's an electron, right? Because it's actually taking this electron from the inner shells of the atom. It's taking it into it, and it actually absorbs it into the nucleus. So I know that because this is on the left-hand side of the equation, that it has to be electron capture. The only other one that it could be would be beta minus, but if it was beta minus, it would have the beta minus particle over here. That beta minus, you're actually emitting that beta minus particle. So you'll have one like that. I'm pretty sure there's one like that where I just ask you, what type of decay is this? You'll have a question like this where I ask you, in electron capture, or in beta minus decay, or in beta plus decay, or in alpha decay, what happens? In electron capture, the nucleus takes an electron from an inner orbital. The other questions that I might ask, I say in alpha decay, what happens? The nucleus emits an alpha particle, which is, as you know, a helium atom. That it emits that alpha particle. I'd probably call it helium, or I might call it like alpha 42 or something like that. For beta minus, I would say that the nucleus emits beta minus, or a negative particle, and then for beta plus, I would say that the nucleus emits a positron. Positron is just another word for beta plus. Okay? So you'll have a question like that, where I just want you to know, be able to describe in words these various decays. Okay, here's another one. What does this nuclear decay equation represent? It's alpha, and I know it's alpha because of that. That should always stand out to you. That big old helium atom is an alpha decay. So you'll have several like that, where you just have to identify the type of decay, or identify the type of the product of it. You'll also have one like this, where you have to apply those conservation rules, where here I know I have 14 plus 0, so that matches. And here 6 is equal to 7. This has to be minus 1, because 6 is equal to 7 minus 1. By the way, what type of decay is this? What do y'all think? So I know that this is a minus 1. And because it's minus 1, that limits me to 2. That limits me to electron capture or beta minus decay. Which is it? It's beta minus. The reason it's beta minus is because this is on the right-hand side of the equation. If that electron was over here, then that would be electron capture. Okay, it'd have a different product too, right? It would have, number 5, it'd have boron. Okay? What is U? So here, for example, this, I don't know why I put U there, but I could ask you, what is the product of here? And I would just give you like an X right there. I just made a mistake. I have uranium for some reason. I don't know why. So what would be the product of this reaction, this decay? Huh? Look at my thing. So I know it has to be atomic number of 7. And so what is that? I'll say that, I forget. Yeah, so nitrogen. So it would be N. Because this is equal to 7. I look on my periodic table and I see an N, or I might give it to you in words, nitrogen. You'll have a periodic table with the names of the atoms on it, so you don't need to know all the names to this. I think I stick mainly sort of to the lower rows, or I might get up in there in that upper right-hand portion. As always, if you have any issues during the exam, you can always ask me to clarify things. I'm not going to answer questions that are, that I expect you to know. But if it's just a clarification, if you feel like you're just stuck and you just really need something clarified, ask me, right? What's the worst that can happen? Sorry, I can't answer that. But yeah, by all means, please do ask me. I encourage you to do so. Oh, here's another example. Radium-224 emits an alpha particle. So you should be able to tell what it is right off. But do you know what it's going to be? Radon, right. The reason I know it's radon is because I'm emitting this helium-4 2. That means that the atomic mass number, which is what I have here, has to decrease by 4. And so 224 minus 4 gives me 220. I think, where is radium? Yeah, radium's number 88 over there. So you see radium goes from 88 to 86. So I'm going from an atomic number of 88 to 86. So my atomic mass is decreasing by 4, going from 224 to 220. My number of protons goes from 88 to 86 because it drops by 2. Knowing your nuclear notation will really help on that, and then just knowing how to interpret these decays will help too. This is a good example of what you'll have on the test tomorrow. What kind of nuclear decay is this? Number 42. Beta plus, and I know because it has this positive one right here. That's the key thing. It's either beta plus or beta minus or electron capture. Electron capture, the electron will be on the left-hand side. Beta plus and beta minus, they're both on the right-hand side, but one's positive and one's negative. Okay, you'll have one like this too, like number 40. How many neutrons? If I have 238, oh yeah, so if I have 146 neutrons in U-238, uranium-238, how many are in the nucleus of U-235? What? I was asking. Oh, well, you can just, there are 92 protons in uranium, so you say 235 minus 92, and that's 143. I say, you might not know that there are 92 protons in uranium, but it is number 92 on the periodic table, so that's how we know. And this number right here tells you the number of neutrons plus the number of protons. So if I want to know the number of neutrons, I subtract the total, the atomic mass number, minus the number of protons. You're going to have to do that. Okay? That's probably like one of the only math problems that you'll have to do, is subtracting those things. Okay? So you know atomic notation. That. Let's look at, yeah, Hannah. What particles emitted? Well, right away, if I look at this, I know it has to be what? I'm looking at these two numbers right here. It has to be alpha, because notice I have a drop in the atomic mass number of 4. That means that I'm emitting this big ol' honkin' alpha particle. It's a big ol' particle, and that makes my atomic mass drop by 4. So this has to be alpha. The way you can, the alpha should stand out to you because you're changing the mass by a lot, or you're changing the atomic number by 2, right? So it's the only one that does that. All the others change it by 1. Okay, good questions. This is a good one. Make sure you can go through and do these. And look back at your test. If you understand all these, you'll be fine on the nuclear decay. But there are a lot of those, so make sure you're good on those. When we look at the light thing, actually, I'll just do it right here. So you're going to have a problem where I show you a ray of light that either bends towards the normal or away from the normal. And a couple things you'll need to know. How do the indices of refraction change, and how do the speeds change? And to do so, you'll need to think about the wave fronts. Right? That's that wave front idea of light we use to think about refraction. And what happens to it? So right here, that light is going to slow down. That means that it keeps going fast up here, and that's what causes it to bend in this direction. Remember we talked about like a twin propeller boat or a tank or whatever? If you want to go turn in one direction, you make one side go faster than the other. So if I ask about the velocity, if I call this V1 and this V2, V1 is bigger than V2. It's traveling faster in the top medium. And if I ask about N1 and N2, well, in slow mediums, like N2, the index of refraction is bigger than it is in fast mediums. I always remember that in a vacuum, N is equal to 1, and N only goes up from there. It doesn't get smaller than 1. It's never smaller than 1. N only increases. As you move into other media, the index of refraction will increase. So you definitely have a question like that. I might two, maybe two, I'm not sure, asking about the speed and or the index of refraction and how it changes. Now notice too that if I switch the direction of this, and there are only 2 scenarios, right? Where instead of moving towards it, I move away from it. If this is N1, this is N2, V1, V2, I do my wavefront. Oh, this speeds up, so this is fast. This is slow. This means this has a small n, and this has a big n. Okay, so N1 is bigger than N2, V2 is bigger than V1. Notice those are switched, that they're inversely related to one another. That N is equal to C divided by V. That's on your equation sheet, but notice that N and V are inversely related. Okay, you will have to calculate V, by the way. If I want to calculate the speed of light, C divided by N. Say, for example, N is equal to 2. This is going to be equal to 3 times 10 to the 8th divided by 2. 3 divided by 2 is 1.5 times 10 to the 8th meters per second. Okay? It won't be any more complicated. Like the numbers will be fairly straightforward. Honestly, I'm probably either going to give you n equal 2, n equal 3, or n equal 1.5, because those are all numbers that just work well with that. If n was equal to 3, what would the speed be? What's the speed if the index of refraction is equal to 3? What's the speed of light? 1 times 10 to the 8th. And if it's 1.5, well, what's 3 divided by 1.5? 2, right? 3 over 1.5, 1.5 goes twice into 3. So don't be scared by the math. I know that some of you struggle with math, but do whatever you need to do to do those operations. Yeah, Danny?
You would determine if the top and the bottom half is fast or slow. How did you determine that?
Oh, So how do I tell if it's fast or slow? I have to go, and I'm going to redraw this, to think about my wavefront idea of light. So if it's bending towards the normal, I imagine this front of waves. And at this point, I ask what happens to make it turn around, to make it turn in this direction. In order for that to happen, it has to slow down at this point. Right? Like if you're in a car and you're driving along the road and your car goes off the road and your front wheel hits a mud, like a big mud puddle or whatever, it slows down on this side, and on this side it keeps going fast, and that's why you veer towards the ditch, which hopefully you don't go in the ditch. But that's what happens, right? That one side slows down and the other side speeds up or stays fast, and so you bend towards the bayou. And a similar thing here. In order for this wavefront to turn towards the normal, to turn in this direction, it slows down here. That means this side is slow and this side is fast. Okay? And if it's slow, that means I got a big N. That's what big N means, that my light is traveling more slower. And if it's fast, that means I have a small N. Okay? Gonna have to do that. I'm gonna give you a diagram that looks like this and ask you something about the index and the speed. It's just one or two questions, so don't.
I just like that because you usually have the like the index with like air, water, glass.
Oh, sure.
Yeah, that's why.
Right, and I'll probably have that too. I might give you that and ask you, hey, what way does the light bend? Let's try that. Let's say that I'm moving from air to water in this direction. What's it going to do? Is it going to bend towards or away from the normal? Well, we draw our wavefront. You ask, so what does it do when it goes from air to water? Does it slow down or speed up? What does it do when light moves from air to water? Does it slow down or speed up? Now, I will tell you that n is equal to 1 and n is equal to 1.3 here. It slows down when it enters water. So does it bend away from or towards the normal? Towards is right. It slows down here. It goes fast here. That means this side sort of swings around, and it's like you run into the ditch, okay, in your car. All right?
I have one more question about that.
Yeah, go ahead.
Will you always have like the N visible for us to see, or we supposed to know the water has?
Oh, no. You don't need to know the index of water or the index of glass or the index of air. I don't think you need to know that. I'm pretty sure not. You do need to know that the index of a vacuum is 1, okay? And any medium above that is bigger than 1. All right, the index of refraction is always less than 1. I'm pretty sure I don't require you to know that of water or glass, but if somehow it slipped through, you can ask me. All right? Okay. What else, y'all? Particular questions or just topics that you want to look at in a little more detail? Those are good ones. Yeah. Oh, no. You do not need to know the difference between a neutrino or anti-neutrino. I mean, as long as you just, that's the symbol, right? If it has a bar or whatever, you don't need to know that. Yeah, that is in the equation. I might ask you, I think in the past I've asked questions like what does the neutrino do? It takes away momentum and energy. We talked about that in class. That they didn't really know that they existed until they had to account for this lost energy or momentum. Okay? All right. Other questions? Or just topics? Single words?
Can we, I just laughed. Can we look at the eye diagram? Like, needle in the eye?
The eye diagram? I think I know what you're talking about. Oh, the parts of the eye?
Yeah, yeah.
Yeah, because you're gonna have it, right? That's electricity. Yeah, there's actually quite a lot of questions about the eye. I think there are 7 or 8 questions. I just got, I don't know, excited about it when I started writing the questions. So you'll have a diagram of this, and they're numbered like they have been on past exams. And I'll ask you, I don't know, what part is actually detects the light for the eye, and that would be the retina. That would be this part of the eye. Like that's where it collects the light and detects it. Or what changes the shape of the lens? That would be the ciliary. Or what is the aperture? That would be the pupil. The aperture that prevents. What did we talk about? Spherical aberration. We did, yeah. Or where does most of the refraction occur? That would be the cornea. Okay. So you need to know all the different parts and what they do and what their name, the names of those parts. I think most of you had this. Excuse me, in A and P, right? Y'all covered the eye. Yeah, but nothing more than what's in the notes. Let's see, what else do we have on the eye? Yeah, make sure you know the 3 layers: the sensory, the fibrous, and the vascular. I think I did have a question actually about this part is this part of the eye, this number on the eye is part of the fibrous, vascular, or sensory layer. Okay, so know where all those different parts fit in. It'll be good to focus on that because like I said there are a lot of questions, more than I usually give. But I usually give a lot of questions on that. I want you to know all those different parts.
The fibrous layer would be considered the cornea.
Yeah, the cornea is part of the fibrous layer. The cornea and the sclera. Because the cornea, it's like the outside part. And so the cornea is the furthest outside the eye. And that's also where most of the refraction occurs, right? When light moves into the eye, most of the refraction occurs at the cornea. Okay. Good questions, all of these. All of it's on the test. I don't think I've said anything that's not on the test. It's everything that we've done. 48 questions. You'll have 2 hours, but it probably won't take you more than 45 minutes to an hour. But you'll have the full 2 hours. Any other questions, y'all? What are you going to bring to me tomorrow? Oh, no, I'm sorry. You don't need to bring your paper. Okay, I know I said that somewhere that you should print out your paper, but I've gotten used to grading it on the computer.
So we don't have to print all that?
No, you don't. I'll send an email out. But what are you going to bring to me? The book. And what are you not going to get if you don't bring me your book? A grade, right. Okay? All right, folks. I appreciate y'all coming. It's more fun, okay?